All right, I want to show you some more examples of using identities. And right now what we're going to do with identities is simply take moderately complicated and sometimes quite complicated trigonometric expressions, algebraic expressions involving trig functions, and simplify them. And the main thing is just to believe that it can be done. To realize that trig identities give you ways to take things that look complicated and actually are surprisingly simple. So I showed in the previous video, this number 2, just how a product of trig functions can actually be maybe just one of the standard 6 trig functions. Our goal is usually to write things as simply as possible in terms of just one of the standard 6 or maybe 2 of the standard 6, and with no fractions and no products if it's at all possible. So here's another one where there's a few strategies we could use, but one of them is to just write it all in terms of cosine and sine. So tangent is sine over cosine, and cosecant is 1 over sine. Let me make that big. And we see that the sines cancel, and so we just get 1 over cosine. Let me kind of do that in a cheating way here. Okay. And that's going to be secant theta. And so that's not obvious if you haven't played with these before. That tan times cosecant, oh, that's secant. Oh, that's kind of weird, but it's a true fact. Secant over cosecant, that's a similar thing we can look at. Let me just grab that, it's going to be quicker. So that's going to be, let's see, secant by definition is 1 over cosine. Cosecant is 1 over sine, but then I'm going to flip it. And guess what? That's tan. So those are just using the reciprocal identities to simplify stuff involving tan and secant and cosecant and stuff like that. Well, here's an example of using a Pythagorean identity. We talked about in the last video how 1 plus tangent squared is equal to secant squared. So this is cosine squared times secant squared. Oh, wait a minute. What the heck is that? That's cosine squared times 1 over cosine squared. And that's equal to 1. So that's a little surprising. I can make this bigger now. So when you see this complicated expression in the middle of some algebra involving trig functions, it's a very, very good thing, because in fact it's just equal to 1. That's a classic example of something that looks complicated. And imagine, what you really want to imagine is this is not the last step in your problem. This is the first step. The boss says, okay, graph this function and graph this function times something else and divide by something else. And it's really good to first realize, you know what, that thing looks like it's going to be a complicated part of a bigger puzzle, but you know what, whatever else there is that might be complicated, this is not complicated. It's just equal to 1. So here's another one. This is a great example of pattern recognition. We want to be looking out for those Pythagorean identities, and what we see is we've got a sine squared and we've got a plus. If we could get cosine squared plus sine squared somehow, oh wait a minute, is there something I can do to break this apart? Oh, I can factor out a cosine. So all of your standard algebra skills are going to come into play here. It's going to be really good workout with those algebra skills because it's in a new context. This makes it harder, but it also really cements those algebra skills much better. So in fact, this is cosine x times cosine squared plus sine squared, and there's a really good reason for writing it that way, because that's just 1. And so this is secretly just cosine x. That is not something that we've ever seen before. Doesn't have an analog in terms of like polynomials, x's and y's and stuff like that. It's special to cosine and sine and the Pythagorean situation. Here's something that's a little different. We had done a bit about what happens if you look at the unit circle and you do things like flip from plus to minus. So let me bring up the sketchpad here again. If you look at the unit circle and we look at this point and we flip it over. Oh wait, no, we're flipping, sorry, it's minus. We have theta or we have minus theta. We can think about what happens. Well, the x values of those 2 points are the same. and even they're the same sign. It's not just the same distance, but it's the same direction as well. So the cosine of theta and minus theta are going to be equal. Okay, so let me do that as a little primer here. Cosine of minus theta is the same, no matter what theta is, as cosine theta. Now this says that cosine is an even function. So the terminology is pretty important, but the more important is knowing that this is a true fact about cosine and knowing that it comes from the geometry. Well, if that's true of cosine, then the same thing is going to be true of 1 over cosine. So actually, let me display it. It's going to be better. 1 over cosine of minus theta is 1 over cosine of theta, or in other words, secant of minus theta equals secant of theta. Secant is also an even function. So that means that this gets to be simplified right away. Let me put this in the display. It's going to be easier. So that's going to be tan x over secant x. And then we can do what we want with it. Well, we got some success before by putting everything in terms of sine and cosine. And we'll talk about when to do that and when it's not really that appropriate. Okay, so now that's going to, the bottom's going to flip. I'm dividing fractions, so that's times cosine x over 1. You just kind of want to be real careful about that. Aha! The cosines cancel, and that's sine x. And so that's actually not nearly as complicated as it seemed. So this is a different kind of identity that we're using here. It's an identity that says if you mess with what's inside, sometimes things simplify. And we've seen that with like pi minus theta, pi over 2 minus theta. We're going to get a lot more practice with those. They all come from the unit circle and the geometry of the unit circle. And then the other kinds of identities are more about what's happening on the outside. If I go back up to like our standard identity, this is you take sine theta and cosine theta, and you're not messing with the theta on the inside. You're doing a square on the outside of the sine or on the outside of the cosine. But both kinds of identities exist, and they're both really, really useful. And sometimes they can get mixed together. Okay, let me just do a couple more examples. Let me pause and see how much time I have. Okay. So let's look at this one. Secant x minus cosine x over tan x. Well, we don't immediately see any patterns. So let me actually just put that displayed. Okay. We don't immediately see any patterns of sine theta, cosine theta, or 1 plus tan, or something like that. And so it's not unreasonable to put it in terms of sine and cosine. Okay, so now we get a line on something. Okay, I've got cosine x in the denominator here, cosine x in the denominator here. That might be nice if I can get this whole thing on the top to be sensible. Whenever you're subtracting or adding with fractions, it's a very reasonable thing to just put it over a common denominator. So let's just copy and paste that sucker. So this is going to be cosine squared divided by cosine. And now I've got cosine, cosine, cosine all on the bottom. So what I can do is I can just multiply by cosine x on the top and on the bottom. So what's that going to be on the top? It's going to kill the cosine. And on the bottom, it's going to kill the cosine on the bottom. So what I've just done is I've multiplied. Let me just write that in. What I multiplied was cosine x over cosine x. That cancels on the bottom. It cancels all this stuff on the top. And now that is something that's very significant. 1 minus cosine squared, I talked about way back up here. 1 minus cosine squared is just sine squared. And you might have thought, oh, what a big deal. That's not a big simplification. But it can be, because it depends on what it's interacting with. Now, so that's going to be sine squared x on the top over sine x. And suddenly that cancels, and that's just down to sine x again. And so this is a more complicated one, definitely, where we had to use some definitional identities, or in other words, reciprocal identities, and then do some real honest-to-God algebra, then again use a trig identity, and namely Pythagoras. This is really the archetypal problem That's the problem you want to be able to do. It's not the first problem you do, but it's a great problem. Now, here's another one, just to finish up. That sine x divided by 1 over sine x. Boy, you can't see that. Because I didn't display it. There we go. And then plus cosine x over 1 over cosine x. I don't want to give you the impression that we always put things in terms of sine and cosine, but usually, I'll give you some hints on that. Usually, if you have any more than like 3 different trig functions mixed together, you usually want to just put everything in terms of sine and cosine. And I'll talk about some cases where you wouldn't do that. Okay, sine x divided by a fraction. Hey, that's just sine x times sine x. That's sine squared x. Cosine x divided by 1 over, that's just times cosine. Hey, that's cosine squared x. And guess what? That's equal to 1. So this thing that seemed really complicated in terms of 4 different trig functions is secretly just the constant function 1. And that's a good example of how this kind of stuff can simplify.